Okay, welcome everyone to our first Origins seminar of the fall semester. I'm really pleased to see so many of you found your way here despite the new time and classes starting again. So before I introduce today's speaker, I just want to remind everybody that you should try to hold your questions until the end of the talk. If, however, you absolutely must ask a clarifying question, please put it into the Zoom chat and I will ask it to the speaker. So today's speaker is Jeremy Dietrich, who got his bachelor's degree in astrophysics and physics from Harvard and is currently a graduate student here at the University of Arizona working with Daniel Apai on exoplanets, and he is going to talk to us today about the hunt for missing planets. So Jeremy, if you want to share your slides, and I'll hand it over to you.
Okay. Everyone can see this, I hope. Thank you. And thank you very much for your introduction, Camber. Hello, everyone. Thank you all for coming. As Camber said, in this talk, I will discuss my recent work in collaboration with Professor Daniel Apai on finding the missing worlds. It's an integrated analysis looking for previously undiscovered exoplanets in multi-planet systems and its applications. This work is part of the Earths and Other Solar Systems project, which is led partially by the University of Arizona Steward Observatory, of which I am a member, and part of NASA's Nexus for Planetary System Science. I'd like to start by showing just how many multi-planet systems Kepler found in both its primary survey and its extended K2 mission. In just multi-planet systems alone, Kepler discovered at least 1,500 exoplanets across more than 500 such systems. And the known orbital architectures and planet natures are shown here in this recent Kepler orrery video from the retirement of Kepler in 2018. Most systems we now know likely contain more than one planet. However, due to the observational biases that limit our search, the data we can gather from these systems are often incomplete. From what we can observe, we can make very specific statements regarding the parameters of these systems, but we still only have a partial view. In particular, why are there systems with large gaps between planets, such as these from the first Kepler data release? And can we continue to probe these systems beyond the outermost known planets to see what we can find? In general, the scientific question motivating the work talk is what is the true nature of the orbital architectures for multi-planet systems? Now, this can be broken down slightly with a few additional, more specific questions. Are there any more planets beyond the known ones? What physical characteristics can we determine for all planets in the system? And do any of them carry the potential for habitability? I'd like to give an example of a multi-planet system and some things of what we know about it. So here are just some of the planetary parameters for the system around the nearby K-dwarf HD 219134, the subject of 3 detailed studies to date. There were up to 7 planet candidates described by the radial velocity measurements in its discovery. Of these, 5 have been confirmed, 1 was discarded, and 1 remains unconfirmed. Periods and minimum masses were constrained from RV measurements, and the 2 innermost planets were found to transit by Spitzer and also later by TESS, giving insight into their inclinations, radii, and true masses. But, as was evidenced by the question marks in that table on the previous slide, we don't know everything about that subset of values for those planets. we aren't yet able to determine the inclination, radius, and true mass of the non-transiting planets. We don't know the likelihood of whether the unconfirmed candidate, G, is a planet, as it was found in one study, but not the others. And there is a large gap between the outermost planet candidate at a period of 94 days and the gas giant planet at an orbital period of 6.1 years. So could we find more planets in that gap and beyond? To answer these questions, we created the Dynamical Multi-planet Injection Tester, or DYNAMITE. Using DYNAMITE, we perform an integrated analysis of the system that builds up multi-planet systems to match the expected orbital architectures that we gather from statistical populations. With DYNAMITE, we can predict the presence of additional planets in these multi-planet systems and the distributions of these specific planet parameters, orbital period, planet radius, when available, otherwise planet mass, and orbital inclination. From these, we can also determine the likelihood that the system contains a planet in the habitable zone around the star, and what the nature of said planet would likely be. DYNAMITE is open source and is available on GitHub at the above link. A description of DYNAMITE can be found on the EUS website, and the DYNAMITE paper has been published in the Astronomical Journal. In the coming slides, I'll describe our goals in creating DYNAMITE, how it works, and the powerful predictive results we generate for a variety of different multi-planet systems. The main goals we set out to achieve are to provide testable predictions on the presence and parameters of hidden worlds in these multi-planet systems. From these predictions, we can gather insight on the nature of the full orbital architecture and planet parameters in the system. In particular, these predictions are testable by current or near future observation techniques. We give best estimates for the physical and orbital parameters and their predicted or observable signatures. As such, we hope to be able to guide follow-up observing strategies like the TESS Follow-up Observing Program, TFOP, as well as inform future missions to assess habitability of exoplanets by providing more exciting targets to be characterized. The DYNAMITE algorithm starts by gathering the known specific yet incomplete data from multi-planet systems. We are able to test DYNAMITE on multi-planet systems both individually and in ensembles to gain knowledge either on a specific system or the most likely distribution from a larger sample. For each system, gather the orbital period, planet radius or mass, and inclination for each known planet in the system. These are the parameters for which we will determine the most likely estimates for the additional planets. In addition, we also gather the stellar parameters. Stellar radius is used to determine the observable transit depth. The stellar mass is required to determine the orbital semi-major axis for each planet. And the temperature, which is used in combination with the other parameters to define the habitable zone for the star. For most of our systems, the data for all these parameters comes from the NASA Exoplanet Archive, while TESS candidate-specific information is gathered from the TFOP archive. Next, we utilize statistical distributions derived from population-level explanatory statistics to test the planet parameter likelihoods. We can assess multiple models for each parameter, as these provide predictions that can be tested via future observational evidence. We aggregate the data from a large sample of known planetary systems and create statistical models that describe those distributions from which the parameters in these models can be drawn. Currently, the largest and most complete sample of exoplanets is the Kepler population, gathered across about a decade of observations. This here is just a small subset shown in the farewell dedication sent out by NASA upon Kepler's retirement in late 2018. So one of the big assumptions we make in the statistical formalism for DYNAMITE is that the distributions of those three planet parameters, orbital period, planet radius, orbital inclination, are functionally independent, and therefore we can separate the likelihood function into its parameter components. While correlations have been found between these parameters, they are relatively weak, and the physical mechanisms underpinning these correlations are not yet fully understood. Therefore, these correlations are not well reflected quantifiably in current models, and we use this to justify our current assumption of independence. However, we stress that this assumption is an approximation, and specifically one that can be tested and revised as observations are compared to our predictions and as more refined statistical models are able to quantify these correlations. For the orbital inclination, there exists a degeneracy on both sides of 90 degrees, as the transit signature for a planet orbiting at an inclination less than 90 degrees would have the same transit signal as a planet orbiting at an inclination of 180 minus that inclination. Most planets are reported assuming their inclination is less than 90 degrees. But we only assume that one planet in the system has 90 degrees, has inclination less than 90 degrees, and we can iterate the remaining planets through the population level statistical distribution to determine the most likely invariable plane of the system. And from there, use the mutual inclination distribution to draw more parameters. For the planet periods, we assume planets can be found between orbital periods of 0.5 to 730 days. These are limited by the constraints on the Kepler planet occurrence rates. For the planet radii, we work with the sub-gas giant population of planets up to 5 Earth radii. There is an observed break in the planet radii above 4 Earth radii, which suggests a different model might better fit that subsample. Therefore, we currently disregard systems containing planets larger than 5 Earth radius. We utilized a Rayleigh distribution for the mutual inclination of the planets when the multiplicity of the system was greater than or equal to 4 planets. For systems with 2 or 3 planets, we instead distributed a scaled fraction of planets isotropically in inclination to test the Kepler dichotomy, which is a measured excess of singly transiting systems. In the graphic here, we show the assumption where there is a low mutual inclination in high multiplicity systems and more highly inclined planets in systems with less planets. Viewing the top system's edge on, we would see all 3 planets, whereas the bottom system would only see 1 planet, even from a variety of viewing angles. For the planet radii, we follow the distribution from the exoplanet system simulator, or SysSim, where the planet radii for a given system are clustered in log normal distributions, allowing for separate clusters when necessary. We also assessed 2 different models for distributions for the orbital period. The first was from the Exoplanet Population Observation Simulator, or EPOS, and found that planets tended to have equal period ratios between them. The second was from SysSim, and found that planets tended to be clustered together in a log normal distribution. As stated before, the differences between these predictions can be tested via comparison to observations for our predictions. So once we have the statistical distributions for the 3 planet parameters, we also add in a simple model for the dynamical stability of the system, given the separation between planet orbits in mutual Hill radii. Specifically, for each test planet orbit, we calculate the separation in mutual Hill radii between it and the nearest known planet or planets in the system. This requires the mass of each planet, which is usually gathered from the known or predicted planet radius and a mass radius relationship. For each pair of known and test planet, we state that if the separation is greater than 8 mutual Hill radii, the test orbit is dynamically stable. If it is less than 8 mutual Hill radii, it is not stable, and the planets will likely scatter. Therefore, the probability of finding a planet within that in period space would be 0. This is admittedly a very simple model, but it does match the data well. Once we have the distributions combined with the dynamical stability criterion, we perform an integrated analysis using the Monte Carlo method to randomly sample the planet parameter distributions and determine the value for the maximum likelihood for each. The resulting likelihood is normalized to 1 injected planet per system to make the statement if an additional planet were to be found in this system, the maximum likelihood value for that parameter distribution is the best estimate for the predicted planet parameter value. And we sample the parameter distribution 10,000 times to build up the posterior distributions. Finally, we output the predictions from the Monte Carlo analysis for each planet parameter, as well as the observational signatures that such a planet would produce, so that the predictions can be tested by follow-up observations. Going back to the example system, HD 219134 from before, this is Dynamite's output prediction for the likelihood in log period space using the equal period ratio prescription. You can see the known planets in green, where the transiting planets are given as circles and the non-transiting planets as triangles. The unconfirmed planet candidate is represented by a gold diamond. Here we omit the greater than 6-year orbit gas giant planet, as we are limiting our study to planets with orbits less than 2 years currently. The posterior distribution and its PDF are shown in the blue bins and orange line, and the habitable zone for the star is represented by the light green band on the right. Focusing on this inner system, we find that with this model, 95% of the integrated probability interior to the outermost confirmed planet D is centered in the gap between planet C at an orbital period of 6.76 days and planet F, orbital period of 22.7 days. This peaks at roughly 12.4 days. And this is the highest relative likelihood in the system for period. So we predict a planet there, which we call HD 219134 PXP1, or predicted exoplanet 1. When we add in this additional inserted planet to the system and run Dynamite again, we find now that a large majority of the relative likelihood lies external to the outermost known planet D. This means the system of currently 5 planets, this inner system, is dynamically packed out to planet D. In addition, the location of the next peak coincides nicely with the position of the unconfirmed planet candidate G. This would continue the dynamical packing of the system out beyond planet D. Now, if we add in planet candidate G to the system and rerun Dynamite again, we find the next peak of the distribution to lie squarely in the habitable zone of the star. Thus, if an additional planet were to exist beyond the 5 in the inner system that we know and the 1 inserted at 12.5 days, we would expect it to be located in the habitable zone of the star. In addition, for this system, the inner transiting planets B and C are rocky, but it is most likely that the outermost planets are more massive and would contain a volatile-rich gaseous envelope. The K-dwarf host star would not be able to strip these planets of their atmosphere through stellar radiation. And so from this, we can determine the likely natures of PXP1 and any other additional planets we might find in the HD 219134 system. To test the sensitivity of Dynamite, we removed 1 known planet from a multi-planet system. We also wanted to test the robustness as well. So we compared Dynamite predictions for the parameters of an additional planet in a system with a known removed planet or varying pairs of planets when testing robustness. Here, we tested the removal of Kepler-154f from the Kepler-154 planetary system. Kepler-154f was the last planet verified in the system and is also the smallest planet. It has a period of 9.92 days and a planet radius of 1.55 Earth radii. When we removed it from the Kepler-154 system and ran Dynamite, we saw that 97% of the integrated injection probability interior to planet C was in the gap where planet F had been removed. In addition, the peak in the log period likelihood space matched the planet period within a couple of hours. Here, I show the planet data with uncertainty ellipses against the bin Dynamite predictions for the planet radius and the planet inclination. The predictions do show good agreement with the known data, as more than 2/3 of the planet radius predictions fall within 3 sigma of the known value. The inclination matches within a couple of degrees, and to the level of informing future observations of the target, this agreement is strong. Good predictions need to identify whether transits are likely and constrain the degeneracy on M sin I for RV planets, which this level of agreement would do. For our robustness check, we also tested removing 2 planets from the TOI 174 system, shown here again with the equal period ratio prescription. In this plot, we see 2 large peaks where the 2 planets were removed, showing a decent match to the removed periods. When we instead switch the 2 removed planets, we see there's still a good probability of finding a planet interior to the current first planet in the system, and the likelihood of finding the middle planet removed is also still there. Interestingly, the overall relative likelihood goes down when we remove the middle 2 planets, and the peak gets spread out in the log likelihood space between the 2 main planets. This is a consequence of running DYNAMITE looking simply for 1 additional planet and determining the likelihood based on that. This rounded and spread out peak in a period ratio gap of factor roughly 8 shows the relatively low likelihood of having 2 planets with period ratios of, say, 2 and 4 or 3 and 2.67, as compared to the Kepler period ratio mean of roughly 1.9, which this model uses. This contributes to the flattening of the relative probability peak, as seen here. However, when we run DYNAMITE on that same subset of planets from TOI 174 and allow for 2 injected planets, calculating the probability iteratively, this is the relative likelihood that appears. Here we see 2 distinct peaks, which better match the position of the 2 missing planets. So from this, we can deduce that gaps in the period ratio of roughly 8 likely are missing 2 planets. So in conclusion, our sensitivity and robustness test showed our integrated analysis predicts the periods and sizes of removed planets with a high degree of accuracy and is robust to changes of the system parameters. So we ran DYNAMITE on a large subsample of the TESS multi-planet systems. Specifically, all the systems as of March 2020 with at least 2 planets, where each of the planets was less than 5 Earth radii in size. On the left, we show period radius predictions, showing that a large set of currently unknown planets would be predicted to exist with orbital periods between 10 and 30 days and planet radii less than 2.5 Earth radii for these TESS systems. The figure on the right shows the probability for each of these systems in the subsample, shown with log period space. They are sorted by increasing first planet period and with relative planet sizes matching the marker sizes. There is tentative evidence for a couple of these TESS systems for additional planets in the TESS archival data. The signals for these orbital periods match our predictions within a few percent. The predicted planets would very likely transit based on our inclination estimates, which matches the fact that we can see transit evidence in the TESS data. And the planet radii are also well matched via the transit depth. Focused follow-up observations from chief-op observers and other programs can confirm these candidates, guided by the predictions that we can produce. In short, our integrated analysis provides powerful, testable, valuable predictions on these interesting and important TESS multi-planet systems. Our predictions are already being tested on TESS and even K2 data as well. Now, I would like to discuss the focus study that we performed on the Tau Ceti planetary system, the results of which are submitted in a paper to the Astronomical Journal, currently under review. The Tau Ceti system has constantly been a home to extraterrestrial civilizations in science fiction. In The Expanse, the behemoth interstellar colony ship Nauvoo, shown here dwarfing the 15,000 population construction platform Tycho station, was bound for Tau Ceti to establish a new human civilization on one of the habitable planets there. In Star Trek, Captain Picard was known to frequent an exotic bar in the Tau Ceti system before becoming a Starfleet captain. In Arthur C. Clarke's Rama cycle, the end destination of the third Raman cylindrical ship was this tetrahedral Raman node in the Tau Ceti system, which was set up to research any intelligent life capable of even primitive spaceflight. Other famous sci-fi authors like Isaac Asimov, Ursula K. Le Guin, Robert Heinlein have also touted the potential habitability of any planets to be found in the Tau Ceti system. So why is Tau Ceti such a hotbed for potentially habitable planets in science fiction? Well, at only 3.65 parsecs away, Tau Ceti is one of the closest stars to the Sun in the nearest 20 stellar systems. And as a yellow dwarf of spectral type G8V, it is the second closest Sun-like star after Alpha Centauri A, and the closest single Sun-like star. As a late G-type star, it is slightly smaller and is found to be less active than our Sun, as depicted in the artist's illustration here. Now, astronomers as far back as the 1950s have noted the similarities between the Sun and Tau Ceti and stated that it would be a good environment for hosting a potentially habitable exoplanet. As such, it was a high priority target for the search for extraterrestrial intelligence even before planets were discovered orbiting it, only in the last decade. So again, here is a subset of information describing what we know about the planetary system that is pertinent to how we run Dynamite. The Tau Ceti planetary system happens to be the third closest confirmed multi-planet system in the NASA Exoplanet Archive. And the current orbital architecture consists of 4 known planets, G, H, E, and F, with periods between 20 and 640 days, and M sin I values between 1.75 and 4 Earth masses. There are also 3 unconfirmed candidates in the inner system, B, C, and D, with periods between 14 and 94 days, and M sin I values between 2 and 3.6 Earth masses. There's also an unconfirmed Jovian analog in a multi-year orbit with weak constraints on the possible parameters, and a large debris disk exterior to all the planets, with a measured inclination of about 35 degrees. However, again, we still have a lot we can learn about the Tau Ceti planetary system. The signals for planet candidates B through D were not found with enough significance in the 2017 study, but they were not ruled out either. Since this system is entirely discovered through RV measurements, we have no known planet radii or inclination measurements, and the true masses of the planets are unknown due to the M sin I degeneracy. Because of this, we do not know if the planets are rocky super-Earths or gaseous Neptune-type planets. Also, even though the system has already been reported with 8 possible planet candidates, could there be more to be found? Our main assumption for the analysis of Tau Ceti is that the planet's orbital inclination is roughly equal to that of the debris disk at 35 degrees. The relatively low spin rate for Tau Ceti suggests a closer to face-on rotation, and with no large rotation axis, and with no large misalignments known specifically between any debris disk and any corresponding planetary system, we justify this assumption as having little effect on the analysis. The planet masses, therefore, would then be 1 divided by the sine of 35 degrees, or about 1.75 times their measured M sin I values. This means that the planets and candidates in the inner system are roughly 3 to 7 times as massive as the Earth. Now, we disregard the unconfirmed gas giant in the outer system as the parameter constraints are too loose for any meaningful predictions and the orbital period is way too long. We report planet mass throughout our study as the radius cannot be determined directly, i.e. through transit measurements. So we convert to radius and back for statistical distribution purposes through mass-radius relationships. And we utilize multiple MR relationships to allow for a more complete understanding of the system. And so here we show our predictions for the Tau Ceti system using the equal period ratio prescription. This is the same as the previous plot with us, where the non-transiting known planets are in green triangles and the unconfirmed planet candidates are in gold diamonds. In log period space, we see that there are 3 predicted exoplanets, Tau Ceti PXP 1 through 3, that closely align with the unconfirmed candidates B through D. There is, however, an additional 4th predicted exoplanet, PXP 4, that does not have a previously detected counterpart. This planet is predicted to exist with a period of 322 days, right in the middle of the habitable zone of this sun-like star. Both the 2013 and 2017 studies mention a signal near that peak in the distribution at 315 or 318 days, respectively. But they cannot fully distinguish the signal from the noise and note it is a possible yearly alias due to the Earth's orbit around the sun. However, the support for this orbital configuration remains true for both orbital period distributions used in this study, with only slight differences between the 2 models for the unconfirmed planet candidates B through D. However, this model does predict PXP4 to be much further out in the habitable zone at a period of roughly 470 days, which is as dynamically close to planet F as possible using our simple model. This leaves room in the habitable zone between planet E and the predicted PXP4 for even another additional predicted exoplanet. Indeed, once we add in all of the unconfirmed candidates, as well as PXP4 to the system, and rerun DYNAMITE again with this model, we find another additional predicted exoplanet, PXP5, can exist near the inner edge of the habitable zone. This would result in a dynamically packed 9-planet inner system, which would be the first of its kind known. And this also, disregards the possible Jovian analog much further out. And so with 2 possible habitable zone planets, this would certainly renew interest in searching for extraterrestrial life around Tau Ceti. But would those planets be rocky? We find that it is likely that the inner 3 planets and candidates, B, G, and H, with m sin I values between less than 2, would be rocky, as at an inclination of 35 degrees, they would fall below the reasonable cutoff for volatile-rich planets at roughly 5 Earth masses. The outer 4 planets and candidates C through F would likely be in a transition region between rocky and volatile-rich planets at 5 to 7 Earth masses. We tested a dual power law mass radius relationship that separates these 2 populations in the transition region. Here, we show the results if all of the known planets and candidates in the system were rocky. The predictions show that any additional planets would also very likely be rocky. However, if the outer planets contained a volatile-rich gaseous envelope, then this plot shows that there is roughly equal probability that additional planets in the system would be rocky super-Earths or gaseous sub-Neptunes. In addition, the inner rocky planet candidates, as stated, are inside the stellar irradiation limit. So previously gaseous planets there would have had their atmospheres stripped by the harsh radiation from Tau Ceti, leaving behind only a rocky core. Therefore, combining the results from the 2 plots, we really currently cannot differentiate between a system filled with entirely rocky planets or a system with entirely gaseous planets where the innermost ones lost their atmospheres. Still, by using the predictions from DYNAMITE, we provide support for the 3 unconfirmed planet candidates in the inner system and predict 1 to 2 previously unknown planets in the habitable zone between planets E and F. The inner planets are currently probably rocky, whereas the outer planets possibly contain a gaseous envelope. We still cannot differentiate between entirely rocky or entirely volatile-rich. However, we do state additional predicted planets would likely follow the same distribution in planet nature as the known planets in the system. In conclusion, we find that Tau Ceti could harbor 3 to 5 more planets than currently known, with 1 to 2 of those in the habitable zone, and would again be a prime target for Ceti if those planets could be rocky and therefore potentially habitable. So the science use cases that we present for DYNAMITE reflect our goals in creating it. We can use DYNAMITE to predict currently unknown planets and also provide support for unconfirmed planet candidates in multi-planet systems, as we have shown for HD 219134 and Tau Ceti. On a large scale, we can inform follow-up observation programs for large surveys like TESS to optimize the planetary yield. Furthermore, we can characterize planetary system architectures based on the probability for habitable planets, which would provide targets for future mission concepts to do precisely that. Large-scale mission concepts proposed for the coming decades, like LUVOIR and the Nautilus Deep Space Observatory, would attempt to characterize the nature of 100 to 1,000 Earth-like planets. However, due to the large scope of these ambitious observations, they would need a dedicated list of targets that are known to be similar to Earth. Therefore, systems where we can predict rocky planets in the habitable zone will be rigorously analyzed to provide potential targets for these next-generation concepts. So I will conclude my talk with a summary. We use DYNAMITE to perform an integrated analysis on multi-planet systems, searching for previously undetected worlds. Our testable predictions can provide for optimized follow-up, especially for large surveys like TESS. Our predictions from our focus study on the Ceti system support 3 unconfirmed planet candidates, as well as 1 to 2 additional, possibly rocky planets in the habitable zone. And we can provide target analysis for next generation mission concepts like LUVOIR and Nautilus. With Nexus starting up the Quantitative Habitability Science Working Group, or QuantHab, this month, we're excited to continue to develop and expand DYNAMITE as a part of the working group. And also, this work is a direct link to the upcoming Alien Earth proposal for Nexus. And so with that, I will conclude and take any questions.
All right, thank you so much, Jeremy. If you have questions for the speaker, please use the raise hand feature under the participants tab. If you are unable to ask a question verbally, then you can write it in the chat and I will ask it for you. All right, questions for Jeremy. Ben.
Hi, Jeremy. Nice talk. I think in one slide you show us the testing using DYNAMITE for many different systems, right? And you show the predicted radius and the period plots with the contour plots.
This one.
Yeah, this one. Yes. Yeah, I think this is very interesting. I wonder that if we can test this by have a statistical analysis, assuming that they are following this period radius 2D distribution, can we push down the sensitivity limit by having by statistical analysis all the systems together, assuming they follow this kind of distribution on your left plot here? Because like for single system, we don't see them, maybe because the signal noise ratio is too low, but maybe together we can push further down the sensitivity limit based on your prediction. Can you test this prediction?
That's a good question. I think if we were to comb through the archival data and combine it all in a large statistical analysis, we could probably focus on the area here where there's predicted to be a large expectation for planets, and set a more stringent limit on the existence of said planets at those periods and radii in the TESS sample.
All right, additional questions? Max.
Yes, thank you. Very great. Thank you for sharing this. So yeah, my question was similar. Have you, for the Kepler data, have you looked at your predictions of additional planets compared to predictions from TTVs in terms of their masses and periods?
No, we have not specifically done that yet. That is a relatively large sample. That would be a very good statistical analysis to do. So that is definitely something we can look into doing in the near future. But currently, no, we have not done any TTV analysis with the as comparing to the predictions from our code.
All right, Everett.
It's a really cool tool, Jeremy. I was wondering, sorry if I missed this, but how this could plug into Eden and follow up of targets?
Yes. So Project Eden is a survey that looks at nearby nearby star systems searching for planets, and so a few of these, and they also follow up on TESS predictions as well. And so a few of these systems are high priority targets for Project Eden, and we're already in the process of searching for these planets, these predicted planets in, and if we can find any in the TESS archival data as well, then we can use Eden to focus our set of observations on that specific parameter set.
All right, question in the chat from Heis Molders, who asks, have you used DYNAMITE on the solar system planets? Would it predict planets inside of Mercury's orbit?
So yes, we've looked at how it would predict planets in the solar system, mostly in the interiors of the system, because we don't go out beyond 2 years yet. So we basically are limited to looking at Mars and inward. And yes, it would predict multiple planets inside of Mercury's orbit. However, we found it is most likely that there are outlying systems, and we believe that the solar system is one of those outliers, in that there's no planet interior to Mercury is a very unlikely system to occur across all systems that we have tabulated data on. But yes, it would predict multiple planets inside of Mercury's orbit in this case.
All right, next question also comes from the chat from Eric Egel saying, how does your method to predict planets compare with the packed planet hypothesis by E.G. Barnes et al. 2008?
I'm not quite sure I'm familiar with the full description of that hypothesis. But I believe, we try to pack the planets as, not say but the method predicts planets trying to dynamically pack the system. For the equal period ratio models, it does that trying to do it equally spaced. Whereas the clustered periods tends to try to do that by clustering planets together and putting them as close as dynamically possible to previous planets. But eventually, if run iteratively across multiple insertions, it will attempt to pack the system as completely as possible. All
right, next question. By the way, Heis says thank you, very interesting. Next question from Brantley Kearns asking, how long do you expect it to take this technology to be able to assist in the search for Planet 9?
So we're hoping to, in the very near future, expand into outer planetary systems. Unfortunately, right now, as we're limited by the planet occurrence rates, but once we are able to have a decent understanding of that and decent model for that, then we will, expand that as far outward as possible. And then at that point, then we should be able to, we'd have enough statistical knowledge to be able to at least say, okay, hey, we predict, beyond Neptune, there's this planet, and then, or, if we consider that to be Pluto, or if we consider that to be Eris, we would continue outward until we find no known planet out there, and then we say, okay, maybe that is where Planet 9 could be.
Okay, do we have any final questions from for Jeremy? All right, I don't see anything. So in that case, I would invite everyone to unmute themselves and thank Jeremy for an excellent talk. All right, we'll see you back here next week. Thanks, everybody. Or wait, is next week a holiday? In 2 weeks? Not next week. No. Yeah, next week's Labor Day, so in 2 weeks. I'm on top.